So welcome to this segment of our day. This is our Turing Symposium. This is the first Turing Symposium we've had at the University of Waterloo. We have we do have Turing Award winners on campus from time to time, but never in droves or multiples. So today is a rare day where we have two Turing Award winners on campus, and we thought that there may be some interest in bringing people together to have a little symposium. So this is our first Turing Symposium here at the University of Waterloo. My name is Stephen Watt. I'm Dean of the Faculty of Mathematics, within which the David R. Cheriton School of Computer Science lies. I'm delighted that we're holding this symposium. It's in addition to our Wes Graham Symposium, and we have an action-filled day as part of our Convocation Week. One of our partner universities in Korea, Post-Tech University, has a tradition that whenever a Nobel laureate visits campus, they plant a tree. And they've got, well, it's not really a forest going, but they really have a very nice way to commemorate the event. And so this is our way of having a commemoration that would be meaningful to the people who are in the disciplines that are represented by our visitors. The first talk that we will hear from is from Barbara Liskov. Barbara has received honors for her work in many areas, including data abstraction, distributed computing, and fault tolerance. The ideas that she has introduced pervade all of the infrastructure that lies behind modern society. So if you're looking at object orientation, the data abstraction, the fault tolerance, and all the devices that we're using today, those things that we take for granted were largely introduced by Barbara. Our second talk will be from Shafi Goldwasser. Shafi's work includes seminal results in semantically secure probabilistic encryption, pseudorandom functions, and using elliptic curves for primality testing and zero-knowledge proofs. So zero-knowledge proofs are very important in today's electronic commerce, where we want to be able to prove that transactions have happened without, for example, saying how much money one person paid for something, or to know that for sure you lost a bid without actually revealing how much the other parties offered to pay. So we are seeing things today that run from the infrastructure that lies behind our world today to theoretical results that will have impact far into the future. So welcome. I hope you enjoy today's symposium, and I will ask Tamer Ozu to introduce Barbara. Thank you.
Thanks. Thank you, Stephen. It's my great honor to introduce our first speaker, Barbara Liskov. Barbara has been at MIT since 1972 and until her retirement in 2014. She joined MIT following her PhD at Stanford and after a short stint at Mitre Corporation, and stayed at the same place for a long time. As Stephen pointed out, she has many accomplishments, and probably she's best known for her work on software systems design, focusing primarily on making it easy to develop large, complex software systems. Many of us have read her papers, and probably her work on the CLU, CLU language is prominent, and that has had impact on C++, C#, Java, Python, and so on. And then the other work that I know very well is her work on transaction-oriented distributed systems, semantic transaction models, nested transaction models that actually have had significant impact. Her work and her impact, the list is long. Venus operating system, Argus distributed programming system, Byzantine agreement, decentralized flow control, Thor and HARP systems for robust replicated storage, and so on. So she's made significant contributions in many areas. She's received many, many awards, as you can imagine, because this is the Turing Symposium. She won the Turing Award in 2008. She's a member of the U.S. Academy of Engineering and the U.S. Academy of Science and U.S. Academy of Inventors. She has won the IEEE John Voigtman Medal and George Stibitz Computer and Communications Pioneer Award. She's getting an honorary degree along with Shafi tomorrow at our convocation. And she has had other honorary degrees from ETH Zurich, Brown, Northwestern, University of Lugano, CMU, and Technical University of Barcelona. So we're in good company. So, Barbara.
Thanks for that lovely introduction. Great, thank you. I'm going to be talking today about multicore programming. So as you all know, I'm sure, sometime in the early 2000s, multicore machines made their appearance in response to the fact that Moore's law was bottoming out. And so this was going to be a way of getting more power, more computation from computers. And from a software perspective, this was a challenge, because the real question was, how can you write software that takes advantage of all those cores in a way that makes sense? It's easy if you have embarrassing parallelism. It's easy if you could think about each core as doing a different task. But if the things that you're doing require synchronization, then it's a big deal. And I was particularly interested in databases, which I think of as sort of the killer app for this, because they have a lot of synchronization required, a lot of concurrency is useful, and so on. What you want is good performance when there's synchronization, and you also want scalability. You would like the performance that you get at 30 cores to be 30 times as good as what you get at 1 core, more or less. If you can't do better than 1 core, I mean, what was the point? I wasn't working in multicores then. I was just sort of thinking about them. I was working on distributed systems, but one thing that was clear is that they were sort of distributed because they had all these cores and they were connected by what is fundamentally a little network inside the computer. Each one also had a little bit of local memory, what they called a cache. But they had a big difference from distributed systems because the cores could also share memory directly, and they did not fail independently, which was another issue we worry about a lot in distributed systems. The first one is an advantage. The second one actually is an advantage for performance. The second one is actually an advantage for thinking about it, because being able to think about a machine that's either up or down is a lot easier than having to think about machines where pieces are up and down. At any rate, the point is that if you implement programs that don't take advantage of the fact that cores share memory, instead they treat the whole thing as a distributed system, it isn't going to perform all that well. And yet, a lot of the early work in systems that was going on in the 2000s took that position, and wasn't a good idea. So what happened was, in around 2014, Eddie Kohler, who's a researcher in operating systems, stopped by my office and started to talk to me about a system he had designed with some others called Mastery. And Mastery was a key value store. It was an in-memory system that ran on a multi-core machine, and it had really good performance. Eddie wanted to talk to me about some correctness issues he had. So he thought maybe we could think about how do we prove the correctness of the way he was doing things. That's not where we ended up before very long. So what I'm going to talk today about is I'll tell you a little bit about Mastery, Eddie's system, what we did as a result of that, and then what happened after that. And I'll try to make it fast because the time is rather limited. Okay, so it's important when you use a multi-core machine to remember that each core has a cache. And hitting in the cache is very important for performance. And doing something that causes a problem with the cache, like modification, which maybe causes an effect on some other core's cache, can degrade performance significantly. And that's what Eddie and his colleagues were paying a lot of attention to in their work on Mastery. So Mastery is just a tree, and there's nothing really special about it. It's got nodes that allow you to find the records where it's at the end where the data is stored. And there are interior nodes and leaf nodes. And the values that you're interested in are stored in the records. Nothing special there. What was special about mass-tree was the way it did concurrency control. So, you know, the traditional way of doing concurrency control in a system like this is to use reader-writer locks, which allow many readers to be running in parallel, but one writer has control. The problem with reader-writer locks is that every time you do a read, you lock. And a lock is a write, and a write impacts cache performance. So that's not a good idea. So what they set out to do was to try and avoid having any writes for reads. They only have write locks. Okay, and they did this by using, they're implementing, like so many of us do when we're doing low-level systems work in C++, and they have access to the compare and swap, which is the basic machine instruction that you have to build on. Compare and swap works on one memory word. So it gives you an atomic operation on one memory word. But of course, records and tree nodes are composed of many words. So you have to figure out how to take that one word and let it control many words. And the obvious thing that you do is to say you have many words, but the first one is special. It's a kind of control word. That's where you're going to do the control, the compare and swap. And in there, I'm going to have both a lock bit and a version number. So here's how writes work. They set the lock bit. They have to spin if the lock bit is already set. They do the update on all those other words of the node or record. And then at the end, they increment the version number and release the lock. So it's very straightforward. That's just a sort of a normal locking strategy. What's interesting is the reads. What reads do is they look at that lock byte, they spin if it's locked. As soon as they see it's not locked, they read all those words. Okay, but the problem is that while they're reading those words, it could be that some other thread is modifying that thing. And so at the end, they check back to look at that first word to see whether the lock bit is set now or maybe the version number has changed. And if so, they just do it again. So no modifications. And I wrote at the bottom, requires TSO, which is total store order, meaning that if I see something that some other process modified at time T2, then I will definitely see something it did at time T1 when I look at it later. There are a lot of very strange cache management systems proposed for hardware, many of which are not very usable by software, but this one is a pretty good one that's quite usable and also performs well. Okay, so the writes are pessimistic, the reads are optimistic, it's a mix, and you get that no writes for reads. Okay, and by the way, the traditional assumption, this is borne out by lots of use of these systems, is that reads are more common than writes. You know, so reads are going to be happening a lot, so the fact that we're making the reads perform really well is good, and they aren't going to interfere with writes very much, so it's all working really nicely. Okay, so, and then there's a little bit of special stuff about how do you insert new keys. If you think about a tree, in order to insert a key, you have to go down the tree to find the leaf node where the tree belongs. And then you might be able to stick it into that leaf node, or you might have to split that leaf node into two, and then you'll have to also affect the parent and could actually back weight up to the top of the tree. And the question there is, what do? Do you lock on the way down so that everything is fine by the time you get to the bottom? And that's not what they did. They went right down to the bottom. They locked the leaf node. If the key can be inserted in the leaf node, you're all done. So very nice. Every now and then you have to split. In that case, you're going to have to modify the parent too. And so they locked going up the path as far as you needed to do in order to capture the modification. And that's a much more efficient regime. This has to do with not only not setting locks more unnecessarily, but also how long do you hold locks. Okay, so that's mass tree. No deadlocks that way because everybody's doing things in the same order. Okay, so Mehdi's talking to me about mass tree, and I'm actually using this as an opportunity to learn a lot about multi-core machines, which I'd been ignoring. And then sort of my true nature took hold, and I said, okay, what about databases? And databases were in a kind of a strange state at this point. For those of you who are in that field, you know this. Everybody was working on partitioning. So the idea was we can't have a database that just sits out there in the memory and everybody uses it as they will. Instead, let's pre-organize it and organize things so that if we can hit in the partition, if core can hit in the partition that it's in charge of, everything's going to work really well, and then we'll have some way of getting around things if that's not sufficient. So we followed a different approach. Now, the difference between a key value store and a database is databases have transactions. So a key value store lets you put in a new key, take out a key, look up a key. One operation has to be atomic. In a transaction, many operations have to run together as an atomic entity. So I just put that on the board to make sure you could see this transaction had many things going on in it. And we have to make that whole thing run atomically. So it's a harder problem. So just like in Mastery, we set up a system where the database is in primary memory, and it's furthermore running what we call one-shot requests, which means whatever the application is that's using the database, it's submitting an operation saying, run this as a transaction. That whole operation runs as a transaction, and that's the end. So it's not like what used to be called ad hoc computing, where there's some person sitting at a console and they do one thing, and then they do a second thing, and that's part of the same transaction. These are transactions that carry out interesting application operations, and this is typically the way databases are used today. And we had a tree for each table or index. The worker threads ran the requests, and there was one thread per core. So very straightforward. And of course, all the workers shared memory just as in Mastery. So the big deal, the biggest problem we had to worry about, there were others, but this was the most important one, was again, concurrency control. Mastery had a very nice strategy, but those write operations released the lock bit as soon as they finished making the modification, and that's not going to work for transactions. So we could have continued to use locking as a strategy, but first of all, I have to say I have never liked locking. Unlike maybe many people in the database world, I've always been a fan of optimistic concurrency control. And you can see that having locks here is a problem. They're going to be held for much longer, which means the performance is going to go down. There'll be more conflicts, and they can lead to deadlocks. So optimistic concurrency control. And with optimistic concurrency control, what happens is the threads that are running the transactions, they never modify the state while they're running. Instead, they just sort of keep track of what they're doing. They remember, what did I read? They remember, what am I going to write? So they have a read set and a write set, and then at the end, they attempt a commit protocol to see if it's okay to commit. And this is H.T. Kung's original optimistic concurrency control. Okay, so here's the protocol that we came up with. I'm going to have to take a glass of water here. I should have. So what's happened is I've run the transaction like that, so no locks are set. I've just entered the attempt to commit phase. Okay, so the first thing we did is we locked all the objects that were listed in the write set. And we used bounded spinning for that, and if it didn't work out well, we just aborted and retried. Once we had all the locks set, then we verified the read set. And the verification was simply looking at the version numbers of everything that had been read to make sure they hadn't changed. If they changed, that meant something came along and modified something we'd read earlier, and so then in that case we have to abort. If we get through that, then we know the transaction is going to commit, and we choose a transaction identifier for it. And this is a local computation. We just guarantee that this number that we're choosing is greater than every number we observed. And then finally, we update all the objects in the write set using that new number as the version number, and unlock. So that's the whole strategy. And it's very conventional optimistic concurrency control. And there's a whole bunch of other issues I'm not going to talk about, although you have to solve all these things. What I can tell you is they didn't have much impact on performance, even though they're hard ones to work on. Okay, so performance was really good. Okay, so this is a micro benchmark where I'm comparing Mastery and our system called Silo, running very tiny transactions, which means the extra overhead of running transactions is going to be magnified here. And what you see is the lines are pretty much identical and the systems are scalable. This little dotted line here, that's what would have happened in that benchmark had we used a global computation to choose the transaction identifier. I think that's a bogus line, by the way. The problem is it's a micro benchmark.
Could
Yeah.
cut off on the border.
Oh, it says throughput transactions per second. Okay, that's, so yes, throughput on the left, and number of threads on the bottom, yeah. And all I'm saying about that dotted line is that this is a micro benchmark. So you're doing almost nothing, and everyone requires what's effectively a global write, and that's a problem. But in truth, of course, transactions typically do a whole bunch of stuff, and so that extra overhead really doesn't matter. It's very important when you do experiments to be careful about what you're measuring, and that's exactly the kind of result that can throw you off. Okay, the other thing I'm going to show you is a performance experiment versus HStore, which was sort of what was going on in database systems at the time. Mike Stonebreaker was the one who sort of came out and said, we're going to have to partition the database. And this is in line with those early papers I'm telling you about in the 2000s, when this was kind of the way things were thinking about database systems. And so, you know, that's a good question. He had a partition. HStore was a clever system. It partitioned, had really fast performance when the partitioning worked, and if a transaction had to use more than one partition, things were not so great. And here's the comparison. This is just to show you that, yes, HStore does much better than our system when partitioning works, but HStore bottoms out as soon as partitioning doesn't work, and we get actually good performance sort of across the line. So it turns out this is really a much better approach. And the interesting thing about this paper was it's turned out to be important because it's changed what's been going on in database systems. People now are working on systems that are like this in the sense that all the cores are sharing memory and they're using memory in a direct way like we are. You know, they're looking at other details like how do you do the concurrency control and other sorts of things. Okay, so this was Silo. And while we were sort of wrapping up this work, I saw something that, in retrospect, it took me an awful long time to see, given who I am, and that is that we were getting all the good performance in Silo from a data type. Okay, we had a very clever implementation of trees, and all the concurrency control that we were using in those trees is what really made the difference. And so why stop at trees? You know, why not support this ability for other data types? And in fact, we would have liked to have other data types because it's very nice to have hash tables in a database. So, you know, silo trees, they're just an abstract data type. And once you start thinking about things as data types, you know you have a specification. And you're looking at the specification in isolation of any implementation details, you can figure out what kinds of concurrency is possible for that data type. And you can even change the interface in ways that increase the concurrency. And of course, what we're implementing with trees is really just a map. It's a map from keys to values. There's a lot of concurrency possible in that. It's just that silo trees took advantage of a lot of that concurrency. Okay, and this is not new stuff. Bill Weil wrote this paper in 1988 when he was a student in my group at MIT, just saying. And because we were looking at distributed systems and we were thinking about things like commutativity. And you know, just the point is, once you start to think about things as data types, you can look at the specification, figure out a lot about what kinds of performance flexibility you have, and then you can take advantage of that inside the implementation, provided the implementation is hidden. And all the concurrency control is done inside. Totally, you know, closed up, yep. Okay, so here's a vision for concurrency control. This is not our vision, it's a little bit of our vision. The applications run transactions. This is the vision of transactional memory. Our addition to this is that they do it by using transaction-aware data types. And they can be whatever is convenient for the application. And what we're really doing here is we're moving transactional memory up a level. Transactional memory talks about having the hardware or the software manage concurrency control one word at a time, or maybe in a group of words at a time, but completely semantics free, all based on just the blocks of memory. What we're doing is we're saying we're going to take advantage of semantics because the data types are going to do the work. Here's just an example, another transaction. This is the old chestnut from databases of moving money from one bank account to another, and you want to make sure that nobody is able to observe the situation when the money's out of one account and hasn't gotten into the other one yet. Okay. So this is what we decided to do. And it took us quite a while to figure out how to organize things so they really worked out nicely and simply. But what we did in the end was we broke Silo into two parts, a platform and then the data types themselves. And we called the system STO for software transactional objects. And so I'm just going to tell you a little bit about how this worked. The platform knows how to run transactions, but it doesn't understand anything about their semantics. So all it does is it provides a way for the data types to record information about the transaction state, like what have I read, what have I written. So there's read and write sets there. And it provides the commit protocol, but since it doesn't understand what's going on, it does this all by callbacks up to the operations of the data type. And so it turns out to be a simple structure in the end. And the data types are the other half of the story. Of course, they have an outward-facing interface. Like in the case of our maps, you could look up, update, insert, delete, and do ranges. But they also interact with the platform as they run those operations by calling, add this to the read set, tell me what's in the read set, stuff like that. And then at the end, they provide the operations that are going to be called back. So these are the operations that are provided, and all the semantics is hidden inside those operations. So what you can see is they kind of fit into this protocol. So we start off by locking. Well, that's an upcall to the lock operation of every object that's listed in the write set. Okay, then we verify the version number of the read set. And again, that's done by an upcall now to the check operation, which looks at each read object to make sure that things are okay. Then the system selects the transaction identifier, and then it updates the object by making an upcall to the install operation. So that's where you know about what it means to install. And then it releases locks by making another upcall. So, and a point that I want to make for you, I'm not going to give you examples of this, is that in Silo, check and install were kind of stupid. So check was always, has the version number changed? And install was always take the stuff I stored previously and slap it on top. You don't have to be so stupid here anymore. For example, even if a version number has changed, it might still be okay to continue because the meaning is still acceptable. Maybe all you really care about is that the balance is big enough to take out the amount that's being withdrawn. And it doesn't matter if somebody's done something to that account in the meantime. And update can also be smart. In fact, one of the things we found to be particularly useful is that if you have commutative updates, like you're incrementing a value, and the transaction doesn't look at what the old value was, you don't have to do that work while the transaction is running at all. You can push that entirely into the commit phase and get rid of all sorts of not only conflicts, but extra computation. Okay, so they can be clever. Now, there was one more operation that I didn't mention, and that's this cleanup. So I showed you sort of a one-to-one relationship between the operations, except there was one I didn't mention. And cleanup is the extra operation. This turned out to be important for us to recognize. It's used for aborts and after commits. Now, you might think we don't need anything for aborts, because after all, you don't do anything in this system until the end, and if you haven't done anything, then there's no work to do. But in fact, we allow you to do stuff in the beginning of the middle of the transaction if you want. And we do inserts that way. So when we insert, we actually put that stuff into the tree, and if that insert transaction should abort, we have to take it out later. And it turns out that's important for performance. So that's another way that you have a lot of flexibility here. The other place we use it is for cleaning up after commit. So think for a minute about what it means to delete a key. So that transaction commits, but removing a key is expensive because you don't actually know where the node that contains the key is. By the time you get around to deleting it, the structure of the tree may have changed, and so you're actually going to have to walk the tree to find the node that contains the key to get rid of it. So we don't do that. What we do instead is we mark the record as being deleted, And then after the transaction's finished, we do this extra work lazily of getting rid of the key entry in the node. Okay, so the performance was good. I'm not really a performance person, or I like performance to be good, but it's not sort of my main motivation. One thing that was really interesting was how much smaller the system got. So Silo was 7,000 lines of code. Now, mind you, we had a graduate student working with us, and he was kind of a, I don't know how to describe him. He's really smart, but he was just doing stuff. And maybe the stuff he did, if he thought a little more carefully before he did it, would have come out a little differently. So we were anyway doing a re-implementation, so we got to rethink some of this stuff, and we cleaned a bunch of stuff up. But even so it turned out to be smaller. So it turned out that making the separation between the types and the platform helped us think things through in a much better way. We could focus in the platform on what optimization issues really mattered for that. We could focus in the data types on what really mattered for their performance. And in the end, we ended up with much smaller code. And we were able to use hash tables as well as trees because now we have this technology that makes it easy to add another data type. And don't pay much attention to the fact that there are many lines here. The main point is the new system performed better than the old one. And our goal had been, let's not do worse. We thought we might do worse because there's sort of extra overhead here and these upcalls and stuff like that. But it turned out to not be the case, and we did get quite a benefit out of the hash trees. Okay, so I just want to conclude, and I seem to be ahead of time, by making a few observations. And actually, these are observations about programming languages, okay? So this work depended on abstract data types. And it's a very good way to go. Better performance by taking advantage of abstract data types. And actually, if you look at what's gone on in computer science, what you see are libraries of abstract data types with very sophisticated concurrent implementations. But they weren't doing that in the transactional arena. It was only for sort of single-use operations. And so all we're saying here is, let's do that for transaction-aware data types too. Of course, not all types give you a big bang for concurrency, but these workhorse types like hash tables, trees, and so forth, they give you a lot of concurrency possibilities. So better performance by taking advantage of semantics. That's a really big win for abstract data types. And concurrency control should be the job of the implementation. I mean, we're depending on a concurrency control regimen here that isn't like what people did before. The stuff they were doing in mastery is not like what was happening before then. This business about no writes for reads and so forth and so on. A couple of years ago, I gave a talk at the history of SOSP. There was the 50th year of the founding of SOSP, the Systems Conference. And so what I did was I looked back over the work that had happened in the early days. And it was really interesting to do that because in the early days of SOSP, an awful lot of programming language work was going on in SOSP. So the paper, Tony Hoare's paper on monitors was there. And also, I think it was Dijkstra's paper on commuting sequential processes was there. And Weir wrote a paper on anyway, there were a lot of programming language papers there. I'd sort of forgotten that they were there. And the reason they were there, of course, was because we were working on operating systems. And operating systems have a lot of concurrency, and they're hard to implement. And people were thinking about, what's the right structure for implementing them, and what kind of programming language would help. And one of the things that came out of that work was Tony Hoare's paper on monitors. And in my opinion, he got one thing right and one thing wrong. Okay, the thing he got right was you want encapsulation. His idea about a monitor was it was a block of code. It was completely invisible on the inside to whatever was using it on the outside. And that's very important. What he got wrong was he predicated a particular kind of concurrency control. The idea in monitors was the monitor got a lock as soon as the operation started to run, and this led to all sorts of problems, like you had to call out and maybe it was going to be held for a long time, or you ended up with a deadlock because the thing you called out to somehow or other got back to you. And later there was a language called Euclid, not Euclid, I've forgotten the name of the language, just developed at Xerox PARC that tried to fix up some of those problems. But I think, in fact, a much better idea is just don't do anything. What you really want is encapsulation enforced by the programming language and just leave it open for the implementation to do what it needs to do in order to get the performance. And the sad part about this story is programming languages are not enforcing encapsulation. And it's really a shame because when you think about big software systems, the system's quality is only as good as the weakest person on the team. And these are languages that don't enforce encapsulation, which means that people who don't really understand what they're doing violate it. And without encapsulation, you can't do stuff like this, the system breaks, just not a good thing. It would be nice if we could figure out how to solve this problem so that not only do we get rid of languages that are well known to cause problems like C and C++, but even Java has this problem. In fact, Java, heaven help us, makes it easy for you to do synchronization from the outside, even though they have a synchronized object that has locks, associated with it. Okay, so that's the end of my little sermon, and thank you. Yeah.
For a very good talk. It was seeing your reference to Bill Weil's work was deja vu all over again. I like that work a lot. It's probably one of the most principled ways of taking into account the semantics of operations in what I call semantic transaction.
Yep.
It's nice to see that it's still alive 30 years after it was published.
Yes.
So, open for questions, please.
We have a question here.
Back when Clyde, when you did the work on abstract data type in the early 70s,
Yes.
did you anticipate all this?
Oh. I certainly knew the importance of encapsulation. And, I went back and read a lot of those old papers when I got the Turing Award, and I'm thinking particularly about Jim Morris's paper. Do you remember that paper?
Yeah.
Right? And he talked about encapsulation. And the point he made in that paper, it wasn't a programming language, and it wasn't quite formed yet what a module was, but the point he made in that paper was the stuff on the outside. His point was, we want to be able to reason about each module independently, right? And his point, yeah.
So in a sense, even though you didn't anticipate specifically this,
Yeah.
because you encapsulated, you were protected against it, so in a sense you did anticipate.
Maybe, okay. Anyway, all I'm saying is I've been trying to tell people, I've been telling people this for years. Encapsulation really matters. In Clue, which was the language I developed, we had automatic encapsulation, but we had a little workaround where if we were working on the platform, we were doing the debugging, which we also implemented in Clue. You can't live with that kind of stuff. And I think it was C# adopted a principle where they said everybody's using encapsulation, but if you're on a particular list, you're allowed to violate it. And I wish programming languages would do that, because every now and then you do have to violate it. It's just that it's violated way more often than it should be. So, but anticipation, no, Anything else? Yes?
So you mentioned the role of encapsulation in enforcing and using the programming language, but what do we do in these days of side channel attacks and things where there are mechanisms not through the programming language to figure out what's going on inside the implementation? If we have an adversarial assignment environment, can we not use encapsulation at all?
Well, first of all, I think you just wandered more into Shafi's domain. But we clearly have a lot of problems that we have to solve. But I think that just because there's a problem over there, that doesn't mean you say you don't want good practice over here. Yeah. And, but I absolutely agree, all those side channels, and I've been doing a lot of work on replication, and the worry there is if all the systems are running the same code, then even having replicas may not protect you against an attack on one computer and stuff like that. There's a lot of other stuff going on. Somebody back there.
Do you see a world without C++, or do you see a world where C++ is better?
Oh, I don't know. I mean, I don't know how this is going to play out. Maybe yeah. And honestly, I invented this Liskov substitution principle, and wouldn't it be nice if that could be enforced by the compiler? So there's a lot of stuff, there's still a lot of interesting stuff to do in the programming language world. And I mean, we use C++ because, of course, when you're doing systems programming, you need that low level. So, but think about higher level languages. And couldn't we do a better job with them? Yeah.
If a monitor doesn't block, how does it describe? Sorry, what does a monitor that doesn't need any of its implementation look like? If the fact that it's blocks is an implementation.
Then it's probably just an abstract data type. It's like a clue cluster, which where the language actually prevents you from seeing the inside, but inside you're in total control. Or think about it as an object-oriented language where there's really encapsulation. So, I mean, you're right. But what I'm saying is it was a sign of the times. And at that time, who knew there were going to be multi-core machines and that we'd want these funny kinds of concurrency control and so forth. So saying that I have a linguistic unit that both has encapsulation and gets the lock seemed like a good thing to do. It's just from today's standard, the encapsulation has endured, but I do not think the lock has.
Any more? Okay, let's thank Barbara again. So I'll invite Shai to introduce our second speaker, Shafi.
Okay, so I'm really happy and honored to have Shafi here today. Okay, so Shafi is she's the RSA professor at MIT. She's also a professor at the Weizmann Institute, and recently she's the director of the Simons Institute for Theoretical Computer Science in Berkeley. And Shafi, of course, as we all know, she has won the Turing Award in 2012 for her contributions to cryptography and complexity theory. She has won the Gödel Prize twice, and she's ACM Grace Hopper Fellow, and she had all the honors that one can think of. I mean, I have a long list here, but I won't bore you with this. I think that for me, what's so special about Shafi is that she really demonstrated in the strongest way the close connection between theory and practice. I mean, on one hand, practical issues in the need for cryptography motivated much of her really deep theoretical work, and then it went back, and this deep theoretical work became key to some of the most practical and popular and useful tools in everyday cryptography. So this is a great demonstration of the connection and interrelationship and useful of collaboration between thinking theoretically and practical point of view. From a personal point of view, I have to share one story. I mean, I met Shafi the first time in University of Toronto in the 87 maybe, and at that time I was just finishing my PhD, and Shafi was a postdoc at MIT, or already a professor at MIT, and she came to give a talk. I finished my PhD at the University in mathematical logic with people who were the leaders of mathematical logic at that time, Shelach and Megiddo, and to me, logic was something for old and smart and mostly already dead people. And then Shafi came very young and fresh, and she invented the new logic. I was shocked. I mean, they invented the idea of interactive proofs, and somehow, it's a word that was laid down by Russell and Gödel and Sir Melo Frankel, and suddenly this young woman comes and says, you know what? I think of logic differently. I think of proofs differently. There could be a completely different way of proofs. I was completely shocked. I think I probably attacked you in the talk, but it's amazing to see how kind of a fresh thinking can revolutionize an area that has been there for so long, and really this idea of interactive proofs became extremely important and useful, and from that grew the idea of zero-knowledge proofs, which plays a key role in cryptography. So it's really a great honor for me to host Shafi here, and we are all happy to and looking forward to your talk.
Hi, everyone, and thanks, Shai, for that lovely introduction. So the title of my talk today is sort of Cryptography for Safe Machine Learning. And as Shai disclosed, I've been in this field for a long time. And I graduated actually with Jeff Shalit from Berkeley, and there he is. We were graduate students together in 1983. Yeah. And then I went to MIT. So having been around for a long time, I've seen a lot of surprising consequences of really very basic and theoretical research in cryptography, as well as other things, but cryptography is my expertise. So for example, obviously all the electronic commerce, the fact that we buy without hesitation, most of us, online and use electronic commerce in every day of life with our banking accounts and so forth, is because we trust that somehow the banks identify us and people are not just stealing our transaction left and right. And that's based really on public key cryptography and the ability to sign, the ability to exchange information freely on the internet without people, supposedly most of the time, being able to eavesdrop. And then these days people are talking about microcurrencies, which are again based on this idea of proofs of work and some sort of a way to commit to transactions without a way to change them. Again, that's based on authentication, hashing, digital signatures. I have a quantum, or some icon for quantum computers, and we'll see in a minute why I also connect that to cryptography. Probably everybody knows here about quantum algorithms for factoring and discrete log. And I think to a large extent that was motivated, that research, by the wish to show that factoring is easy because of the big use of it in cryptography. But there's also other reasons to think about quantum computers in the context of cryptography. And cloud computing, what does that have to do with cryptography? Well, we have this whole idea of maybe doing things in the cloud, but for some reason we trust that the cloud is actually doing what we want. I'm not sure that trust is based on anything. But in any case, you could think about this idea of sort of trust but checks. You'd like to also get a proof that whatever is done in the cloud is what you requested. How would you do such a proof? So as Shai referred to, one way to do a proof is to redo the computation, but then it would be sort of fruitless. It would be pointless to do it in the cloud. So the question is, how can you verify computations quicker than doing them yourselves? And there are these mechanisms of which we call delegation systems, which are essentially interactive ways to verify the correctness of a long computation very quickly with using a lot less resources, which again is sort of an outcome of work that was very basic and theoretical work done in the context of cryptography. And then there's theoretical work that this definition of NP as a probabilistically checkable proofs, a lot of work on pseudorandomness, again, all originating from some simple ideas that had some cryptographic question at heart. So a point about all of this is to say that I think that right now, The next frontier for where cryptography can make a difference is in this idea of cryptography for safe machine learning. And throughout the talk, maybe I will try to explain what I mean by safe machine learning. So safe machine learning is not a crisp definition. There's a lot of problems associated with machine learning that have an element of adversarial settings. So in other words, in cryptography, I think the one thing that unifies all cryptographic work, whether it's pseudorandomness, authentication, or encryption, is there is an adversary out there who's trying to break the system. It could be trying to find out what you're speaking, or trying to pretend to be you, or trying to predict the next supposedly random number, which is pseudorandom, because that's at the heart of security. Or it could be, even in a proof, it could be someone who's trying to convince you of the correctness of a statement, which is incorrect. So you can also think of a proof as a process of convincing someone that you're not a liar, that you're actually proving a correct theorem. So this adversarial thinking, certainly within machine learning, the more it's getting traction and usage, one has to think about means of attacking it, whether it could be at the stage where you're training a machine learning algorithm and you're providing the data, or in the stage later when you're trying to use the machine learning in order to maybe misclassify. So thinking adversarially actually helps making more robust systems. And that's kind of the hallmark of cryptographic thinking. And I think that there's a lot of work in cryptography could enable safe machine learning. And the way to think about safe then, the most general way is that there's some adversary. And you'd like to make sure that the machine learning is working even in the presence of an adversary. And I'll talk about that throughout my talk. So this talk is long and dense. And that's what it is, okay? so with that apology in mind, that's what it's about, and I'm going to start. So essentially, this history of relationship between machine learning and cryptography doesn't start today. That certainly doesn't start with my talk. Even in the 80s, there was a lot of interaction between these two communities, but the interaction was essentially, could be summarized with this one sentence, even though I will speak about it with more content, is that hardness for one was bliss for the other. So when you had concepts which are easy to learn, that meant that they were cryptographically insecure in some sense, and vice versa. So if there were some cryptographic problems which were hard, you could build sort of a concept class which would show some sort of lower bound for machine learning. So it was really an interaction between the two theoretical communities. And I will speak about that. But today, and that's going to be most of my talk, there's been sort of a switch in my mind, and that is that there's starting to be a lot of interaction, but actually progress in cryptography is good for machine learning. So it's sort of, to get to the safe situation in machine learning, you have to use a lot of cryptographic tools. So whereas in theory, we always used to talk about getting impossibility results in machine learning by showing that some cryptographic thing is possible, now the story is completely different. It's all sort of in the positive direction. Okay, so sorry, I have to connect to the power. So machine learning, I'm sure a lot of people in the audience here know a lot more than I do, but this much I do know, and that is that there are lots and lots of models, okay? And depending on the model, there's things that are possible and things that are not possible. So very intuitively, if I want to sort of review what happened in the 80s, let's say that machine learning there's some box, and the box has some algorithm in it. It might be in the C++, or it might be in I can think about it as some sort of DNF formula with logical connectors, in this case in 3 variables, but it's hidden and I don't know how it works. I have some sort of access to this box. Either I get some examples of inputs and outputs from this box. Maybe I can even ask for, I could feed in x1, x2, x3 and get an output. Maybe I even know some partial circuitry, but I don't know all of it. And of course, this box is this magical box that can do many things. Like it could tell me whether a message is spam. In this case, the message is the x1, x2, x3. Whether some tumor is malignant, if the input is some X-ray or MRI. It might be an application to college, and this box is going to decide whether the student will be admitted, whether a bank loan should be approved, suspect released on bail. So you know this from popular press, maybe from your work even. Obviously, it's going to be what we'd like to do is to be able to figure out how this box works. And in order to do that, we need to understand what it means, what we want to learn this box, but we need a definition. So obviously, only if we'll have a definition that we could answer the question whether we can learn or cannot learn, at least in theory. And we need to talk about what kind of query we have to this box. And the paper that started this relationship between, I think started sort of theoretical computational learning and also started the relationship between learning and cryptography is this paper by Valiant in '84, where a theory of the learnable. And in Valiant's model, which is the model I'll just use for the purpose of this part of the talk, is that you're given examples, right? So you're given X and the concept and some label, whether X is in the class or not, and is drawn according to some unknown distribution. You have no idea what the distribution is. And what you'd like to do is to come up with a learning algorithm. We'll generate a hypothesis H, so it's a hypothesis for C. And this hypothesis should agree with C approximately with high probability. So what do they mean? So approximately meaning that the probability that on X it's different should be low. Okay, so it might not agree all the time, so it's just approximate, but at least it should agree with high probability, so most of the time. Okay, and there's an error definition here, and the error is when it doesn't agree. And you want this error to be small. So once you have this definition, you can start asking for particular concept classes which ones can be learned according to its definitions, which ones cannot. And in Valiant's original paper, for example, for that DNF that was in the first slide with the box with the DNF inside of it, he was pretty optimistic that maybe it could be learned just from seeing random examples. So you see sort of the X vector and the value that the box assigns. And it might be a distribution you have no idea about, and you could learn it in polynomial time, say, with a small error and approximately correct. But it turns out that actually it's a very difficult problem. So it's NP hard in the worst case, but in the worst case doesn't interest us so much in the learning. And then there have been a sequence of papers. It took a long time. I think the best result that's known is by Jackson in '94. Where they show that you can actually do this when the distribution is uniform and you are allowed to ask questions and get answers. So you can't just get random samples. And we don't know better results than that. And even though this is the best result that's known, very quickly we, in cryptography, kind of jumped on this definition and showed, you know what, this is a very ambitious definition. We can show you that there are concepts that you will not be able to learn in polynomial time. So provably. What does provably mean? If some cryptographic thing is true. The cryptographic thing is true is, let's say, factoring is hard, for example, or if actually one-way functions exist, so that's more generally than whether factoring is hard. Whether there is some cryptography at all, then this goal that Valiant set is not doable for concepts, for some concepts which obeys definition. So they're sort of polynomial time. This box C has a model which can be valued in polynomial time. And I can actually ask the questions and get back answers. Still, I won't be able to learn it, and even if it's on the uniform distribution. So that's what I was saying here, is that, I think that paper was by Valiant and Kearns in '86. We showed that secure RSA implied the existence of concepts which are actually fairly low complexity classes. So it's something called NCs, so this is low depth circuits. So the box can contain a concept which is very simple. Can be done in parallel, like in log n levels of parallelism, and yet you won't be able to learn it. So it's not that it's just very complicated classes cannot be learned, but even very simple ones. But they, of course, have to be engineered in a particular way. So they embed in them some sort of cryptographic hardness, and that's what makes it hard to learn. And over the years, there were more and more results of this type. In fact, even of 2014, I have a paper with a student and a colleague, Vinod Vaikunthanathan, where we show that even if you can not just, the learner has a lot of things going for it. Not only you can ask questions, you might be able to ask aggregate questions, to ask how many examples are there in certain intervals. So lots and lots of other abilities to play with this box don't help you to learn it. Again, this is because you're developing cryptographically these creatures which are so complicated and allow you so much utility, and yet they're hard to break. And the more utility they're allowed, that sort of is equivalent to sort of being able to access a learning algorithm in a very sophisticated way and still not be able to learn it. So it's not so interesting, in a sense. It sort of makes theoreticians happy because we can make it show that you won't be able to solve the problem, even if your job has become easier for some concepts which nobody wants to really learn, okay? But still, it's what we do, right? We want to show the limits of what can be done. So I just wanted to say that it wasn't just for learning, also for generation. So another problem in learning is you're given this box, you don't want to actually learn it, you want to come up with another box, which you understand its internals, and this other box is kind of equivalent to the previous one. Equivalent in the sense that, let's say the box decided on cats, I don't know why, but there's this obsession with cats in this community, or dogs, or both, or successful college essays, or CVs that gets you a job, or slides for keynote talks, or plays by Shakespeare. And you know this box does it really well. You'd like to come up with another box that does it as well, let's say in an indistinguishable way from the original box. So also that's a task that's hard. We can show things that you can generate that you cannot generate. You can prove cryptographically you cannot generate. Okay, so in this picture, it was all bad news. So here's an interesting thing that happened also sort of in the 90s, and that is a paper that appeared in a crypto conference where machine learning said, okay, you guys have been showing us all kinds of concepts cannot be learned. We're going to return you the favor. Here's a problem that we have thought about in the context of learning theory, and it's a hard problem. Maybe you can use it for building cryptographic systems. So they're saying, you're showing us all the time things that cannot be learned. Good, we're going to show you something that we know cannot be learned, but it comes from our community. It's not based on number theory, it's not based on factoring or discrete log. Maybe you can use it in cryptography to build crypto systems. And it was a problem called learning parity with noise. And in fact, this is an excerpt from that paper. It says, modern cryptography has had considerable impact on the development of computational learning theory. Virtually every interactability result in Valiant's model has its heart in a cryptographic construction. In this paper, we give results in the reverse direction by showing how to construct several cryptographic primitives based on certain assumption on the difficulty of learning. So what is the problem? The problem is this. You are given a bunch of, you know that there's a bunch of equations in these variables, S1 through Sn. You can think of these as 0, 1 variables. And the variables are secret. And somebody tells you, listen, those S1 through Sn are secret, but here's a sequence of constraints that they satisfy. Except, if they really told you what the answers were, then you could use, in some sense, Gaussian elimination, find out the value of this secret S1 through Sn. So they don't give you that, but they take every equation and they flip a coin and decide whether they're going to give you the right answer or flip the answer. And the coin is not 50-50. It's let's say, some probability a third or 1 over n or some probability, okay? And that's why it's called learning parity with noise. So it turns out that depending on the noise, this is an extremely hard problem. Once I put noise in there, even though the answer might be still unique, so there is only S1 through Sn, one unique answer that will satisfy all these equations, it's very hard to find. Maybe there is an algorithm to find it, but as far as we know, the best algorithm is exponential. And this has no factoring, has no discrete log. It just is a particular problem which is very simple to describe and actually works with small numbers, not with large composite numbers. This is all mod 2. And it's difficult. So they say maybe you can use this as a basis to build encryption, as a basis to build digital signatures and so forth. And it seems to be even harder than what we know how to do the factoring. So the best algorithm is really exponential. So there's just a little overlog n here in the exponent. Whereas for factoring, the algorithms, even the ones on classical computers, not on quantum computers, are actually more efficient. And also there were nice worst case to average case reduction for a certain noise level. Okay, but what happened really for cryptography, this motivated another problem, which is called learning with errors, which was introduced by Regev in 2005. And what he said is, you know what, instead of flipping the answers, so taking 0, 1 variables, equations, and then flipping the answer, putting noise, why don't we think about these variables as lying in some finite field, okay, which I called here ZQ. So I have S1 through S4 here, and these guys are not 0, 1, they're just numbers in this interval. So numbers mod Q, smaller than Q. And Q here is 17. And again, there'll be equations in these numbers. And again, I'll put noise on the right-hand side of the equation and tell you what the noise is. Tell you what the answer is with noise. But now the noise, of course, is not 0, 1, because these numbers are larger, so it's some sort of Gaussian noise, okay? And this is certainly harder than learning parity with noise because it generalizes it, so that one is a special case, but it's much easier to work with this for cryptography. So they introduced a new problem based on this learning parity with noise, that Regeb has, and actually showed also that it was equivalent to approximating the size of a shortest vector in a worst case integer lattice. So some of you know what that means, some of you don't. But the point is that this actually links it back to some problem that's sort of natural in mathematics. So it's not a number theory problem, it's a geometry problem where if you could, this is as hard as so that problem is, again, is a hard problem. It's hard in the worst case. And the beauty here is you can show that if you could if you cannot solve it in the worst case, if in fact it is hard inherently, then you have sort of average case examples of this learning with errors. So the coefficients are sort of these equations are random, and the secret is random, and so forth. And those are going to be hard problems. And now there's a lot of structure here. And the structure doesn't disturb disturb us because we can, still the best known algorithm is the same running time as before. But what he did is sort of revolutionize cryptography. There's something called homomorphic encryption. The fact that you can encrypt now in a public key way, but now actually the encryption that you have is you have like encryption of X, encryption of Y. You can get from that the encryption of some arbitrary function of X and Y. So you can work with the encryption without decrypting and computing functions under the encryption. That's something we don't know how to do for number theory. It requires a lot of structure. It's because of the, somehow, it's because of this, it works, okay? So in some sense, these equations are wonderful. We can add, we can multiply, we can get arbitrary functionality on encryptions of different values. And it really was all due to that learning parity with noise introduction in the learning community. And in fact, it has actually quantum significance as well, this new problem, this learning with errors, because as you know, these days, people don't just have a hypothetical model of quantum computer, but they're trying to build it. There's a lot of effort, there's a lot of money by governments, by companies, to try to build a quantum computer. This is the obligatory, oh, no, it's not there. I had this cartoon. It says that we shouldn't worry so much. But the truth is that that's a stupid thing to say. Because who knows, right? In 10, 20, 30 years, we probably do have a reason to worry. And in fact, the NSA and the National Institute of Standards have started planning for post-quantum cryptography. So they don't want to wait till the event that there will be built a quantum computer that could risk the security of existing systems. And there's a call out trying to replace all crypto systems that we're using, let's say, on the internet for signatures, for encryption, and so forth with a quantum safe. And the point is that learning with error problem, we don't know how to solve with quantum computers. So whereas we know how to factor, the best algorithm on quantum computers is the same as the classical. So as far as we know today, there is no breakthrough, and therefore it is sort of safe for quantum, even in the event the quantum computers will be built. Essentially, this is a long process, and there's lots of constructions and capabilities using this sort of geometry or learning with errors instead of number theory, and they're all quantum resilient in the sense of that we don't know of algorithms, like Shor's algorithm, to break them. Okay, so far it's not so happy, right? It's still true that the bliss for cryptography is a nightmare for machine learning and vice versa, okay? And we don't want to be that. And the second part of the talk, I'm going to say that these impossibility results are actually going to be positive news. Okay, so now we're switching to the second part. How much time do I have? That's how much I have, or that's how much I spent? Oh, okay, very good. Okay, so what's the switch over to today? So we know that there's lots of data, and everybody agrees that this is sort of a game changer. And there's access to a lot of data is a game changer. And there are all these areas of life like health, finance, infrastructure, vision, NLP, security, threat prediction that has changed substantially in terms of their practicality. So we can use automated systems to make health predictions, certainly to target us in terms of ads, which is economic growth. And we have these examples of self-driving cars or systems that can really kind of evaluate their surroundings, so vision is improved, NLP is improved. These days, people even talk about doing policing, bail, credit rating, using automated mechanisms, which are based on evaluating a lot of data, historical data of the past. So this is not even just a dream or a nightmare. So I think in New Jersey, they had this algorithm that was helping all courts to set bail. It might have been stopped because there's been a lot of discussions against it. And in New Orleans, I think there was, I read that the police uses this automated systems to decide where to send police cars, so it will be more worth it in terms of arresting people and so forth. So there was actually an interesting workshop last week in the Simons Institute, where I'm directing right now, of sorts. I don't know how much direction it needs, but the workshop was extremely interesting. People, I really encourage you to go and watch the videos. It was all about sort of bias and pointing out, it was really about racial bias, that particular workshop. It was all about pointing out how past data and these systems have a sort of always a variable that's sort of race-related. And it might be directly race-related, or it might be through the zip code or other things that sort of point to race, and that changes how the systems evaluate. Let's say, to release someone on bail, where to send the police. And even though that might be in agreement with what the past data says, this doesn't necessarily mean that the past data was doing the right thing. It says that obviously if you're going to have more police in these neighborhoods, then there'll be more arrests in these neighborhoods. It's just sort of tautological. Maybe there should have been more arrests, maybe there shouldn't. The point is that that's what the data says. There's a lot of question, and even in medical decision making, it was very interesting. There was a whole part of this conference that talked about the fact that genomic research and pharmaceutical research often uses the race variable as a way to, in good faith, to get better medications, let's say for minorities, but it's not so clear that that's really the axis according to which you should think that how you should direct your medical research or the pharmaceuticals. For example, there was an example there that for blood pressure medication, it's well known that African American communities have higher blood pressure. So there is an insert in medication for blood pressure that says instructions for everyone and then for African American, not just American, African American. And that group is so diverse, really genetically speaking. Often if you take two people who are members of what's considered African American, they're more different than what a white and an African American might look like. So that variable is sort of a dominating variable in making decisions. It might not be. It shouldn't be. I mean, that might be true anyway when you go to a doctor, even if it's not automated. But certainly once you put it as part of an automated system and you make sure that every doctor operates that way and doesn't even doubt the material, it's problematic. So that's just saying that there are problems, but it's clear that there's a sudden shift of power from the hands of individuals to the hands of these algorithms. And indeed, there are these statistics about where is the market sitting, and where it used to be in oil companies, these days it's all in the hand of data companies, like Apple and Microsoft and Amazon and Facebook. There's these quotes, data is the new oil, data will become currency. And I guess the point is that it depends how you feel about these companies, but it is the case that having a lot of data and being able to build models based on this data, it's sort of like a train that's going very fast, and one has to sort of think for a minute. And I think a lot of people are feeling that there's sort of going to be two options. One option is that there will be regulations that disallows it. You don't want to do that because there is a lot of progress that can be gotten. So the other option is that there will be some regulation in place or some protection to make sure that things have been considered to some extent when these systems are being built. So where does cryptography come in? So I think that cryptography and cryptography tools have a lot of potential to enable this safe machine learning. And then now I'll explain what I mean by safe machine learning. So we have a lot of models, we have a lot of tools that address sort of correctness and privacy of algorithms. So security here includes both correctness and privacy. And the question is, how can that come to bear on machine learning? So the way that I'll define this safe machine learning, just by going through a sequence of challenges that will make it unsafe, and say why crypto might help it. Any questions? Because I've jumped to second part of the talk. Okay, so obviously, it's sort of immediately, if in fact the power of machine learning comes from data, let's assume that that's the case, that's what it looks like now. Maybe in the future you won't need so much data and you can decide even without any data or with little data, but right now it seems like data is key. The data comes from individuals, or at least from companies that have collected data about individuals, either with permission or not. Then ensuring the privacy of the data and the model will, in some sense, maintain power. Okay? So it seems very obvious that you don't want to give this data out freely, or at least that ensuring its privacy is important at this stage before you give it out. And when I say privacy of the data and the model, data is obvious. Model, I mean the hypothesis that you've learned about the box. So there is a model that you've learned based on playing with this box for a long time, and now it's out there. And this model contains a lot of power, both because you can sort of, it has been shown that you can reverse it. So by using this box, you can actually find input examples how this box was, what was the training. So in machine learning, there's always a training phase where you take the data and then you come up with an hypothesis, and then there's a classifying, which is now you have the hypothesis, you use it in order to classify new data. So what does crypto have to do with it? We'll see a little later in the talk that there's lots and lots of tools in crypto that can do exactly that. So we'll enable you to do training even though your data, without looking at the data, by sort of doing trading in a sense on encrypted data. And also will ensure that you will able to use a model once it's been developed without actually looking at it and experimenting with it freely. The second thing is that these models, I don't think people have really thought about this, but let's say somebody has come up with a model. It's supposed to predict wonderfully things about your health. These models are extremely powerful, right? And you want to make absolutely sure that they cannot be tampered with, nor that they were developed in some way in order to implement a bias. So how do you do that? How do you actually get proofs that a model is consistent with the data? So you just can take it on faith that a company says that's what they did, but it would be good to have some mechanism where you could actually test that out. And you could think about that even as an interactive proof type setting where there is the model owner, there's someone who might have some access to data, limited because they don't have the whole database, but could they use this access to data in order to test that the model really is unbiased and that it's consistent with the data in the way that is claimed. And obviously there's a asymmetry between whoever built the model, so they had access to tons of data, and whoever is testing whether this model is accurate and unbiased. Now what does crypto have to do with it? Again, interactive proofs, checking the correctness of this type of statement with few resources. It's a little different than interactive proofs that we do today because it's not just an input. There's sort of there's this data and you are able to sample it. So it's different resources that the prover and the verifier would have, but we have a lot of skill with working with this asymmetry and working with different resources, and there are already initial works in this direction. Okay, so it's also sort of an opportunity for crypto, obviously, to use all these tools that we developed. Okay, what's another challenge that machine learning talks about a lot today is this adversarial machine learning. So what do we mean here? We mean, let's say there's a box, a machine learning algorithm, you either have black box access to it or not, and your goal now is that you want to misclassify. Why would you want to misclassify? People always talk about the example of a self-driving car, and it's supposed to identify a stop sign, but now it's going to be thinking that it's a yield sign, and then there will be an accident. Again, because you're thinking about an adversarial setting where someone, for some reason, wants to disturb the operation. So the question is, how do you prevent that? So it's a big question in machine learning. And as far as I understand, sort of the best results that are out there, you don't have to read all this, there's some work by a group by Alexander Madry at MIT. There's a lot of work everywhere. But I know more of his work, so I'll describe it. And what he does is he defines a class of specific attacks, like domain-specific attacks. So if you're talking about a machine learning algorithm for vision, for recognizing images, then he says the kind of attacks might be flipping pixels, rotating, things that are natural to the vision domain. And he says, if I know that the adversary is restricted to these type of attacks, then what I'm going to do is I'm going to train the model in the training time, not on really good pictures, but good pictures plus pictures that have been attacked this way. And now I will prove to you that in the classification time, that kind of adversary will not be successful. And if you had another domain, you could consider a different type of attacks. Of course, restricting the attacks is not exactly a worst case adversary. So that is a limitation of this type of approach. But it's very similar to a cryptographic approach. You have an adversary, and then you want to prove that your thing works well with respect to that adversary. Except in crypto, we usually like to talk about a larger class of adversaries, not a restricted class of adversaries. So for example, somebody mentioned side channel attacks. So in cryptography, people have talked about side channel attacks. Can you really hear me? Okay. So they've talked about side channel attacks like taking a crypto system, putting it in a microwave. That's kind of the ridiculous one. But another one is measuring time, how much time the crypto system takes, or power. And that enables you to actually figure out things about the secret key of the crypto system. There's some kind of correlation. And the way that this was remedied is each attack had a protection to it. So against power, you had some protection against power. And against time, you change your crypto system so it always takes the same amount of time regardless of the secret key. And then there was work in the theory community to try and have a definition, a mathematical definition that encapsulates all side channel attacks up to some bound. By saying that no matter what the attack does, you can think of it as leaking some bits in the secret key. And now you want to build a crypto system where even if bits in the secret key leak up to a certain bound, everything leaks, then it's over. The rest of it is not leaked. So that type of approach, maybe for machine learning, trying to generalize a bunch of attacks, which are domain specific, could be useful. But it's more of an inspiration rather than a concrete application of cryptography to machine learning. Really, if we go back to the Debbie Downer picture, I guess the holy grail would be to build machine learning models where misclassification, this adversarial misclassification, would require learning a cryptographically hard task. So somehow embed a cryptographically hard task in your machine learning model and show somehow that if an adversary is trying to attack, he will have to solve this problem as well. It's a holy grail because at the end, machine learning is talking about some natural domains, right? So what's even the ground truth is unclear. So doing CRISP theory work for domains like vision and NLP is very, very difficult. But at least in the theory world, we could think of, of this type of approach. In fact, having said that this is the holy grail, there's a lot of work in the machine learning community now, which is also by people who used to do cryptography. Too many words, I know that, don't read them. Which show that maybe we're too optimistic to think that we can battle this adversarial machine learning in some robust theoretical fashion. So one shows that, this is work by Mahmoudi et al. In a whole bunch of papers which appeared in crypto conferences where they show sort of some machine learning settings where you show that you can always kind of come up with some sort of misclassification. In the sense, theoreticians would like you define some bad property, and you say no matter what you do when you train this model, in the misclassification time, they will be able to give examples where that property takes place, regardless of what your protection is. But these things are parameterized. It's an interesting area of research. Okay, back to another challenge. So a big question is that I've given data, and I was told that everything is done properly, and my data isn't going to leak in a machine learning context. I can trust that Apple and Google and all these people who say that they're using differential privacy. Is that familiar to people? There's a lot of talk now about companies using privacy preserving mechanism on your input data. I can say they use it, but if you talk with anybody from Google from that group, it's sort of similar to this joke that my mother used to tell. It's not my mother, every Jewish mother in Israel. That this woman, she borrows a vase from another woman, or she doesn't borrow it. In any case, the neighbor comes to her and says, where's my vase? So she said, first of all, I never took it. Second of all, I already returned it. Third of all, it was broken. So if you talk to someone, there, they say, well, this is our trust model, but we don't really use it, and if we do use it, it doesn't work, or something of that sort. But there is an effort. But in any case, it would be nice to get a proof that they use it. In fact, there are all these laws, right? In California, there's a big privacy law it guarantees consumers control over data. And now I think they're saying that New York is going to have a law that's even going to be stricter than the California law, and there's the GDPR law in Europe, where they talk about the fact that systems should not be able to point back to an individual. And it would be a very interesting to come up with a privacy mechanism where you could maybe prove it. So you could develop methods to trace your data or verify that some privacy preserving mechanism were used. So if you could come up with a tight definition of privacy so that if you used it, one cannot detect that you didn't. But if you didn't use it, that's the more interesting case, then somebody's identity would sort of be able to be reconstructed. That would be sort of evidence against, yeah?
Privacy mechanism. The person who owns the data or the person who's trying to steal it?
So privacy mechanism, I mean that it could...
Who's using the privacy mechanism?
It's a great question. So if you trust, it's a great question because of the following. What I meant to say was that, let's say Google is using it. So I give them my data, and then they, the way they use it in order to build a machine learning model is using some sort of privacy preserving mechanism, maybe inserting noise into my data, maybe inserting noise into the model. You could imagine a system where I don't trust them and I do it myself. So whenever I contribute a piece of data, I already put noise, and people have done that. It's called local differential privacy. But what happens is that if people put noise locally, they get a lot less utility. So you'd have to put, you'd need a lot more data to get the same kind of prediction if people locally would put noise. So it'd be much more useful if it could be done globally. So you'd trust the centralized place to put privacy mechanism in. Okay. So that's a work in progress. How to come up with definitions which are tighter. Because the definitions that are out there now are such that what you require in terms of privacy is so strong, okay, that even if it's violated, you're not going to be able to detect it. So if you require something so strong, and violation isn't immediately, it's not an if and only if. You might want to require less, but in such a way that you could detect when it's violated. What's another cryptographic type of right, so what about if I have a model? If I invest a lot of money into it, I had a lot of data, a lot of cleverness. Now I'm putting the model out there, and now somebody's going to, change the model a little bit and say that this is theirs, and they want to sell it. So how do you kind of protect the use of your model? And there's an interesting work, actually, that appeared in Usenix 2018. They call turning your weakness into your strength. So their idea is, in the context of deep neural net, they say they want to watermark them so that if somebody else uses it, you could at least notice that they use it. And the way they watermark them is actually very clever. So remember when we talked about adversarial machine learning, adversarial examples. So what they say is, okay, you can do adversarial examples. Let's put some, when I train, I know that there are some examples that will be misclassified. I've kind of planted them, but I planted those examples in a very clever and secretive way. So if somebody steals my model, they're not going to know where those examples are. But I will. So I can go to court and say, hey, you see this model of theirs? It misclassifies big time something that I've inserted. It's very clever. Probably will be broken in the sense that you can get over it. But it's an interesting direction, how to watermark these models. Okay. What else? I talked already about fairness in terms of, to people of different races, accountability of these systems, interpretability. So right now, the way that people define this, I mean, there's a lot of argument about how to define it, but mostly they have this notion that two similar individuals should be treated similarly. And they have a notion of distance between individuals, so in order to talk about similarity. So in cryptography, we have a lot of ways to define similarity, because we took similarity of ciphertext, and in order for security definition for encryption, it's a very different type of definition, which composes. And these definitions don't compose. So the question of coming up with definitions that compose, so if you have 3 different systems, and each one of them have different notions of similarity, and you still want it to use all 3 of them. So in some sense, like a lot of work that was done in programming languages, calling procedures, and if you're going to think of machine learning systems in a larger system being used, you can come up with pathological examples where both of them are fair in some sense, together they completely introduce huge bias. So you'd like to think about how to compose this, and again, there are sort of cryptographic definitions which compose, which might be appropriate. What else? Randomness. So apparently setting the random weights, let's say in a deep neural net, or a lot of machine learning algorithms use randomness, What kind of randomness? Where do they get these randomness? So in crypto, it's very important for us to show that how to generate good randomness for cryptographic purpose. Because if the randomness is bad, then you can predict it, then you can break the entire system. And in fact, there are attacks on the crypto system really through their pseudorandom number generators. And I guess that's an interesting question. What kind of randomness is used in the context of machine learning, and what should be used, et cetera. Defining specialized cryptographic functionalities, well, I'll get to that in a minute. Okay, so there's a real opportunity, in my opinion, to use cryptography for these challenges. But this also all sounds like prophesizing, you know, and it's nice to do it. You know, after you get a Turing Award, everybody has to listen to you, so at least they have to be in the room. But there's actually concrete work that's been done on these challenges, where you actually use crypto in the context of machine learning, and it's all about those first two challenges that I spoke about. You know, ensuring the privacy of the data while you are training and while you're classifying. So I just want to tell you, I have 6 minutes, I'll tell you a little bit what is being done on these challenges. Okay, so essentially, as I said, there's sort of the stage for training, and there's a stage for classifying, and then there's a stage where the model's already there and you might worry about someone stealing it. So these are sort of three concrete problems that people have actually used cryptographic tools to address. I would say that the most amount of work is done on classification, sort of how to classify, and less on training, and I'll speak about each one of them, and model stealing. And really, there's a lot of work. And you know, and they sort of have this kind of flavor where in the beginning you show that it's possible, then you have some asymptotic, efficient, concrete, and now there's systems which are sort of proofs of concept, but they're not really utilized out in application. That's changing as well, but okay, let's talk about classification. Sorry, let's talk about what is these cryptographic tools for a minute. I'm not going to talk about it, just show the picture that that can be used. So the cryptography has been, like, since the 80s, we've developed lots and lots of tools. There's something called garbled circuits, this differential privacy, multi-party computation, where all these people have data and they compute joint function on all their data without revealing the data. There's secret sharing. There's something called homomorphic encryption, which I use in a word, where you can encrypt, and then you can actually run through evaluation on the encryption without decrypting, and then you decrypt the output. If you have the key, you can decrypt. If you don't have the key, you can still do evaluation. So how many of you think this is complete, I don't know, you know, in Hebrew we would say Chinese or Greek? It's Greek to me. And in English you would say it's Chinese to you. But how many of you have seen some of this stuff? How many of you have not seen it and are willing to admit it? Very nice. Okay, well, then you should take a crypto class and see it. No, seriously, there is a lot of here. This is just to indicate that there's a lot of machinery that's been developed. And in particular, if we think about the classification phase, what happens there? You have a training, first there was some training phase that happened. There was a data set, you know, machine learning was working, and then they came out with a hypothesis or a model. And this is held by some sort of server. And then later a user comes, or a client, and they give their data, and it's run, the data is run, and the model then does a prediction. So if you think about it, this stage, this classification stage, you have two parties. Somebody who owns the model, which I call the server, and then you have the client who holds the data. Okay, so there's two parties, and they are going through some sort of exchange, and the server might feel that he doesn't want to give his model away. Maybe it's because it's a hospital and his model is sensitive. Maybe he wants to monetize it. So there might be even regulations, you know, or profit motives. So regulations like HIPAA and so forth on medical information. And the client also has data that you might want to keep private, because there might be credit records, history records, medical records. So we have a classic cryptographic situation. There are two parties, they both have security concerns, but they want something from each other. So in other words, the client wants to be able to predict, use the model, maybe to diagnose them, and the hospital or the server wants to be paid. So they want to give the model away. And that's what we call a two-party two-party computation, sort of special case of many parties, there's just two. So really, we have, in principle, results that enable us to have this done so that at the end, the client will get his diagnosis, the hospital will get paid, and they will know absolutely nothing more than what the diagnosis is and then getting the price. And this is already goes to the 80s. There's this work by Andrew Yao about garbled circuits. The thing is that it's not very efficient. So that's what Shai was saying. I mean, it's very nice, but you can't use it really. So there's sort of these two technologies out there. One is the secure two-party computation from the 80s, from Yao. And then there's more recent work from 2008, which is called homomorphic encryption, where the idea here is that, in some sense, the hospital encrypts the model, the client encrypts the data, and now you have two encrypted things, and then you run sort of a computation on this. So at the end, there's the encryption diagnosis, which the client can decrypt. And they are very different from each other. In some sense here, the computation is costly, but communication is low. And on this side, communication is large, but computation is more efficient. So you've got these two different technologies, and you can use one or the other, depending on what machine learning model you have. And in fact, that's what's been done. So first, the work started with very simple classifiers, like perceptrons or least square or some regression models, which mostly were linear, except for decision trees. And in that case, when the machine learning model is of that nature, you can take two-party protocols and kind of engineer them to be suitable to this, and you get good performance. So in fact, a little bit more than that, you build a few cryptographic primitives of how to do dot products between, let's say, x and y, x held by the model, y held by the client, and you want to do an inner product, or you want to do comparison, or argmax, or decision trees. You optimize these, and then you compose them for the right classifier. And we have built, there was actually a work with Raluca Popa, who was a graduate student at MIT, and this paper was written then. Now she's a faculty at Berkeley, and another master's student, Raphael Bost, which it works. So for example, for just linear separating sets of points, you just need to do dot products and then compare. That would be enough. But you want to do it on encrypted or in a two-party secure computation, and it can be done. Never mind, that's details. But these days, people are talking about neural nets, right? These are much more complicated models. So you have many different levels. If it's deep, there's sort of a linear level followed by a nonlinear level, and the nonlinear has some sort of operation like ReLU or some other very highly nonlinear in the sense that we can't really approximate it with few additions and multiplications. So the question is, that's a dog, right? My dog is much nicer, but in any case, I don't know why. I thought it was kind of a funny picture of that dog on the internet. Right, so there's linear levels, and then there's this nonlinear in the round boxes. Time's up. Okay, I have only like two slides or so, 3 slides. And if you just use these two-party computation, you're going to have very, very high communication if you use just two parties. And so what do you do? There's this interesting work done in Microsoft, Christian Lauder's group, where their idea there is to take these nonlinear levels and to approximate them by low polynomial functions, and to show that the prediction of the network is not so much off. It's close to what the predictions of the network would be with sort of like a ReLU. And that is easier to do, to perform even under encryption. So the big idea here is really that you trade accuracy for efficiency. So once you do it under encryption, it gets much slower. So you're saying, let's trade the accuracy. Anyway, a machine learning model is not perfect. So it's just going to be a little lower accuracy, but in turn, you get privacy. Another approach has been to sort of take these two threads of multi-party computation and homomorphic encryption and use them in alternate levels. So there's this work out of MIT, which called Gazelle by Vinod Vaikuntanathan and Chirag, who was a student, and Anantha Chankad, I can never pronounce his name. He's the dean of engineering at MIT. I should be able to pronounce, how do you pronounce it? Eh? Yeah. Oh, I really never knew how to pronounce it. Okay. It didn't even sound like what it's supposed to sound like. So anyway, they have this work where they alternate using homomorphic encryption and two-party protocols depending on the level. All this to say is that the tools are there. The question is how you put them together. And I think important for machine learning people and crypto people to work together, so to understand the models, to understand what would be a reasonable replacement of machine learning operations by operations which would be friendly for cryptography in the sense that they can be executed more efficiently. So they get pretty good performance. And having said that, I say another thing that's been happening going from theory to practice is, even though I said there's proofs of concepts, there are more and more libraries that are being written for homomorphic encryption, where you have faster and faster performance, and it's done by companies, it's done by individuals at universities, like Picard, that's in the University of Michigan. And it's up to this point now, I think, that you can perform some interesting computations under encryption in a commercial setting. And my prediction is that in 10 years, people will actually do that. But I think privacy security always has this slow uptake from theory to practice, because it's always an added value, right? You want things to be done efficiently. And privacy is sort of a secondary concern. So I think that's true also in the machine learning setting. And I think that's about all I'm going to say. There's some competition. Training. Training is much harder. Because train, you have to use, on encrypted data, you have to do it again and again in phases. So whereas classification takes work, training is much harder. It's still being done. In training also, there's an interesting other direction, and that is, let's assume we're in a setting where the data comes from individuals, and you have to give it, let's say, to Google. Now, how are you going to, why should you give it? Okay. So my point is that the data comes from many different sources rather than from one source. So what the Google is, in a sequence of papers called on federated learning, where the people who are providing the training data are doing a protocol so that the data will get to the server, but without reveal. I know, I'm done. Last slide. So my last slide is that I think that there's a lot of good work to be done. Thank you. So the current systems, it's exactly the same answer. So if you took the model and you just encrypted it, it will give you exactly the same model when you decrypt. I mean, the same answer when you decrypt. What I said is there are some suggestions that in order to make the whole thing more efficient is to replace the model by another model, which doesn't classify maybe as well as the original one, but still now when you encrypt, it will give you the results as this changed model. So the analysis of the accuracy is separate from the whole thing of encryption. But you could, and in fact there is some new work in that direction, come up with an encryption system which is faster and introduces errors. And again, you could say, well, if I can prove that the results are not so far from an encryption system without errors, then it's good enough. So it's an interesting direction that is being pursued. It's a very good question.
Okay, thanks, Shafi, again.
I'm Maura Grossman. I'm a research professor and director of Women in Computer Science. I also have terrible laryngitis, so please bear with me. I'm really honored to be here today to chat with you both. So in researching your backgrounds, I discovered that as undergraduates, you both majored in math and minored in science. And I was wondering who encouraged you to pursue those subjects and what obstacles, if any, you faced in doing so, and whether people encouraged or discouraged you from pursuing graduate studies in STEM.
No one encouraged me, no one discouraged me. I've often asked the question of myself, why was it that so many women who tried to follow the same path that I did turned aside because things happened that caused them to see it wasn't going to work very well. I think maybe I have thick skin, and I always thought of what I wanted to do, and I wasn't going to be deflected by snide remarks or something like that. So.
Hi. So I didn't minor in science, but I did take physics in high school, and it was my favorite subject. And I would say that I was encouraged. I guess my father really, I come from Israel, and at least Israelis at that time were very pragmatic. I think still it's true. So it was very nice to do liberal arts, but they kind of said you have to do something, at least my father did, and I think it was kind of a symptom of the time that if you have to do something that you can sort of eat. in the sense. I mean, in other words, to put food on the table. So my father was very adamant about the fact that I should do physics and mathematics, and I may have done it anyway, but so there was certainly not only encouragement, I would say pushing. And then, you know, he always said that he was right. About Barbara's comment about what is it that makes people do other things, and maybe it's a question of people who've done it, our path is thick skin. I think that it's true. But of course it means that if we take that to an extreme, is that the women who are sort of senior in the field are of a particular type of thick skin, and it would be good that it would be more representative of the population, like in the case of men, I would assume. So you don't have to be thick-skinned so that's an interesting question.
So along the same lines, I assume that through your studies, and at least during some part of your career, you found yourselves predominantly in male environments. And did that ever pose a challenge? How did you deal with being the only woman in the room and looking around, not having mentors or role models? Did you have other mentors, male mentors?
So it was just the status quo. I mean, Shafi's a little younger, so
Right,
things
right.
maybe had gotten a bit better.
Yeah.
But I was an undergraduate at Berkeley, and I was majoring in math, I was minoring in physics, and if there was one other woman in the room when I was taking a class, it was, you know, that was a maximum. And the male professors were not paying attention to me, you know, and it was just, so no, I had no mentor. And I just sort of kept a low profile and did what I wanted to do. And I think things have really improved. So in fact, the women coming in today do not have to be of this type so much as it was the case then.
Yeah,
Yeah.
I agree.
Yeah. I think you have your own mic, so you don't actually have to use it.
Oh, that's true. That's true. Good point. Yeah, I completely agree with Barbara. So I was at Carnegie Mellon, and I wasn't, I remember the first programming class, there were 3 of us. And then in graduate school, there were a few more. And in terms of mentoring, no, I don't think so. I think that we were a large group of students at Berkeley, and we, again, with Jeff and others, and we hung out together, and it was a very friendly group. And I think they were the, you know, the mentoring. So it's not exactly mentor, but it was a support system. But when I came to MIT, Barbara was a mentor. And I think she is largely responsible for me coming to MIT, and or being a faculty at MIT. So the fact that she was there, I think, was very meaningful. I mean, if you were not there, then there would have been no older, you know, other women. I think it was very meaningful, even though we're in different areas, but just having your presence. And I think, and Ron Rivest was a mentor. I mean, he's also had a lot of women graduate students. I mean, if you look at it, so there was something about him that made it comfortable to interact with him and learn from him. Again, it doesn't really mean, mentor doesn't mean someone who explains to you how to do the research, but the existence, in fact, you can come into somebody's office and say, look, I got this issue, and they don't dismiss you. They listen to you. They might disagree with your interpretation. And I think it's better now. I don't think it's great. I do think the women who come are still thick-skinned, but maybe less as the years go by. But now it's very different. I see that I said at MIT, you know, this year at Berkeley, and I saw the faculty recruiting, and it so happened at Berkeley they made 6 offers this year, 5 of them to women, and not because they were women. I mean, they just happened to be the better candidates. So one had to really argue to get the 6 positions, but the first few were women, and as happened at MIT too, a couple of years ago. So there's more graduate students that are women, and they're doing extremely well. It doesn't mean that one is to lose sight of it. So if I look at undergraduates at MIT, there's a lot of undergraduate women, 45% or something? Almost 50% in undergraduate, but at Berkeley, the computer science major has a lot fewer women. Part of it is because California has removed the affirmative action. You're not allowed to do affirmative action in California, and it's a public school, which means that you can't even look at what gender is, and there's some differences apparently that we don't understand exactly and that the results are that the computer science major has fewer women, maybe 20%. So it's an interesting question what to do about that.
So this question's for Barbara. You were accepted at Berkeley, but you decided to go work at MITRE Corporation. And I'm interested in what influenced your decision to enter the work world rather than academics, and what led you back to graduate school later on.
Yeah, first I want to say the percentage of women majoring in computer science at MIT is more than 35%. It's not quite the same
okay.
as the percentage
Total.
but it's still really doing very well. And I think that's true at Stanford also.
They're private institutions. Yeah.
Yeah. And anyway, you wanted to know why did I go to work instead of going on to graduate school. So I graduated in math, and and I realized that I wasn't ready to do a graduate program because it takes a certain kind of dedication to go on to graduate school. You have to admit that you're going to really focus and concentrate and so forth. And maybe deep down inside, I actually knew mathematics I wasn't good enough for mathematics. Mathematics is a highly discriminatory subject. You know, you're either great or you're not good enough. And people come to realize whether they are which category. I don't know whether this is true, but I'm really not a mathematician. So I decided to go to work instead. And that was all there was to it. But because I got a job as a programmer. And you have to understand there was no computer science then. So I didn't know there were computers, and I would never have gotten into computing if I hadn't left school and gotten this job. And so that job opened a door for me that has made a tremendous difference to my life.
This question is for you, Shafi. As Shai mentioned, you've alternated between serving as faculty at MIT, Weitzman Institute, and Simons Institute for Theory of Computing at Berkeley, and more recently, you started a startup called Duality Technologies. So how do you navigate and balance all of this, and what do each of these contribute to your career?
Right, so first of all, the assumption that I navigate and balance is an assumption, right? It's like, with MIT and Weizmann, it was sort of for personal reasons that I alternated the two, and I used to spend like 3-4 years at each place, and then I would come back to MIT and teach 1 term a year. That, required navigating. For example, in teaching, right? So if graduate students, what used to happen is that I would have it happened 3 times, so I could say it's a pattern. They would have like 5 graduate students at MIT, and they would start, and they would get to a place where they're like in their 3rd year or sometimes longer. And then I would move to Israel, and they would come visit me, or they would be co-supervised by someone else, or they would work on their own, and we would Skype. And I guess Skype didn't exist then, so we would email and use phone calls. And it's worked well. So my students have done well. I mean, not every single one of them, but many, many of them. I think that maybe having hands-off supervision wasn't bad for them, especially in the later years when they knew how to do research. It was actually kind of how I was mentored at Berkeley as a graduate student. So it was hands-off, and so that was one way to navigate the student issue. In terms of the company, I truly believe the cryptography can be used in the real world, but I don't think it's going to happen if we just stay in universities. And in cryptography, because of sort of the strong basis in mathematics, you need experts to get the systems that will provide what we claim they provide. And I think that the only way to do it is to have some kind of industry representation. So now there are research groups in Microsoft, in IBM, in VMware. There's specific places that have in the big industry. NTT now is opening a lab at Palo Alto. But startup is the way that I thought of doing it. And also, as a faculty member, you can do it, right? You can do 1 day a year, which is probably what you guys are allowed to do as well, and have the role of a co-founder. It's not like you work on it full time.
So this question is for both of you. How would you explain to a 15-year-old girl what it is you do and why it's important? And how would you capture her imagination and convince her to enter computer science?
I don't think I know how to answer that question. What I can tell you is that at MIT, maybe 15 years ago, we started a summer program for girls from high school to introduce them to, it was done in the ECS department, so it was primarily focused on engineering, electrical engineering and computer science, and they come in for 6 weeks and do projects. And that kind of program is extremely effective at not only sort of sparking their interest. I mean, there are going to be girls who are already sort of interested, but it sparks their interest. They get to see that there are other girls who are also interested in this. They get to see the graduate students and what happens as they go on. So it's a way, I think, very effective way of mentoring. I mean, I don't think me as a person is that important to a 15-year-old girl, but a project, a group, some organization like that, I think, can make a huge difference. And I think many universities have outreach programs like that. Each of us does our own part, both for women and for underrepresented minorities. It does pay out down the line. It gets people interested so that they'll go on.
Right. I don't know. It's a good question. You know, I have a nephew and a son that I'd like to convince to do computer science, but or STEM, and I'm not sure you can. I'm not sure you can convince people to do anything, but maybe you can. Maybe you can make sure that the discussion at the table involves discussion about topics, about science and about technology. I have friends who, what they had is in the bathroom, they were keeping all their science issues. And their children, apparently, when they were, that was the only reading they'd had, looking through science articles. Having said that, they have 3 children and only one of them is doing science, so. Hard to say.
So how has the field of computer science changed since you entered the field?
Tremendously. I was fortunate to enter the field very young, or I mean, when it was a very young field, and there was so much that we didn't know. It was sort of chaotic, but there was wonderful low-hanging fruit. That's probably understates how difficult it was because it was so chaotic, it was kind of hard to see, you know, what was big and what was small. Today, you know, we have a well-developed core understanding of computer science, and we're building stuff that it's amazing. I did my PhD thesis in AI. I was interested in machine learning, but I switched out partly because I didn't think the way they were doing machine learning in those days was going to get anywhere. It was all based on let's try to get the computer to think like a person. And as you know, the way machine learning works is not like that. So that whole business that's going on now, the stuff that Shafi was talking about, you know, that's a huge change. The explosion of the internet that happened in the 1990s was completely unforeseen by everybody I know. It went from we were using computers, we were using them in groups, we were using distributed stuff, and then all of a sudden there was a shift in the whole world where all of a sudden we were in information age instead of being, you know, what we were before. And then the problems started to happen. And if you think about the problems that we're having today, I mean, you're talking about a very important problem, how to make sure that machine learning systems do the right thing. But there's a whole bunch of other problems that are not based on machine learning, they're just based on people misbehaving in ways that people misbehave. And so I would say this is a major challenge of our time, how to cope with that, what we can do to get applications to behave better, to sort of tamp down fake news. I think about this quite a lot. So there's huge opportunities out there. There's a lot of work to do.
Yeah, I was thinking maybe 3 things that I would say. So one thing is about the fact that systems and theory work much closer together today.
And I remember when I came to MIT, so there was a theory group, there was a systems group. I don't think there was a lot of interaction on science. And these days, I go to the systems. We have a group, let's say, that talks about security. So people on the system side that are building systems, and the cryptography people who mostly come from theory. And it's amazing to me that the systems people know the definitions. They want to strive for them. There's a real interaction between the two. And there's a realization that theory is important. In fact, all these algorithmic contributions, like in terms of search, even sort of the PageRank algorithm that Google uses comes from a theoretical community, and these things became the backbone of applications. Same for public key cryptography. So I think theory and systems work together, and I think that's amazing. So it's a good progress or advance. On the other hand, the fact that everybody sees that there's so much application in computer science, there's a sort of a shorter road between making an invention or building a system or coming up with a theory to making it into a product. And I think it has a risk of invading also the way we think about research, like which research problems we choose. That's a good thing, but it's also not a good thing. Because often to do something really innovative, you can't think about whether this is going to make money, whether there's demand for it today. How would you know? So I don't know exactly how to battle that, but that's a difference, which luckily for me, I don't care at this point. I'm at the stage where I want these things to be used, but I think for someone young and ambitious, it's not the right way to think about what research problems to pursue. And I guess the third thing is that Barbara and I were on a panel at MIT recently, is that we all recognize that these computer systems have incredible power. Like in the terms of the fake news, they can change, the world in terms of who gets elected, and with these automated systems, they'll change who gets policed, and we have to kind of say, wait a second, we haven't thought about that. We haven't thought about how to put the measures in. We never thought that a computer program would have the power of a weapon, and it can be. So I think that's a big change.
So for those who want to take the road less traveled, what are some areas in computer science that need more attention, and what are the really big problems that still need to be solved?
Well, I'm not sure there are areas that aren't getting attention. I think the big problems to be solved are actually exactly what we've just been talking about. It seems to be relatively easy to think of a new app or a new service. It's much harder to think about how to do that ethically, how to put it out in a way that avoids misuse, what kinds of misuse. It's almost like the adversarial thinking you were thinking about, except rather than thinking about it that way, you sort of think about it's just a person out there trying to do bad things. I think this is going to require a lot of work. Some of it is not technical. Some of it has to do with laws that need to come along. And I think every new technology ends up with a situation like that where unexpected things happen. But I think there's a lot of technical stuff that could be done also.
Yeah, I agree. I always want to take your mic.
Right.
No, I agree with Barbara. And I guess another thing is that there's a lot of interaction now between, which I saw through the Simons programs, through sciences, like neuroscience, and with computer scientists. I think it's very interesting work, how to either be inspired by what happens in the sciences or work together with them in order to develop a better computer system to do what they need to do. There's, for example, a new program someone is proposing where clinicians will be, people who use data for medicine, but in practice with patients, would work with computer scientists for machine learning. So actually work with them, actually meet with them and talk about what to do. I think interaction with these other fields is a place that it's not commonplace, but I think it will be.
So is there any advice you would offer to our undergrads, grads, and faculty members, something you wish somebody had told you a while back?
Well, I don't know. I can tell you what I advise my undergraduates, and that is you need to, people come into college and they come out of college and they have expectations of what they're going to do, and life doesn't work like that. And sometimes something you think you really would like to do and you would enjoy is not necessarily something you have the talent for. And so you have to walk this path, especially as I think a young post-bachelor's degree person, where you're trying to figure out what is the right thing for you to do. And I think the two things that matter the most are you want to enjoy what you do. Aren't we lucky to be in a field where we can enjoy what we do? But you also have to pay attention to what you have talent for. And where that takes you may not be where you expect it to be, but that's okay. You just have to work it out for yourself.
So what Barbara, I didn't know how to answer your question, but what Barbara said inspired me to think that, we had the luxury of not having everything so well defined for us. And I think these days people seem to feel that when they enter college, they already should know what they're going to do the rest of their lives. And that's absolutely not true. I mean, my son is 19, and he told me the other day that he doesn't know what to do because he's 19 and he doesn't know what he's going to do with the rest of his life. And I was like, but you're 19. It was exactly, so the idea that he was even thinking that he's supposed to know what he's going to do the rest of his life is because we're very job-oriented and all these opportunities. And I think one has to put some time into seeing where your talent takes you. That was a luxury, I think, that we had. So I don't think there's some advice someone could have given me. Maybe they could have said you shouldn't worry so much, but.
So one more question for you, and then we'll open up, see if anyone else has a question. What does the future look like for you? What do you want to do? What do you hope to accomplish? What's still left for you out there?
Well, I actually am officially retired. I'm still working about half-time, which is fun because I enjoy, thinking about technical problems. But I don't feel like, I'm going to pick up some new area and start running with it. But I think Shafi is in a different position. We'll pass it on to her.
Yeah, I don't know. I think it's the same as maybe it was 10 years ago. I want to still be creative, creative in science, creative in, let's say, even in this directorship position. I want to make an impact in the sense of making sure that good science is done, and also personally. And I hope that I can still do it.
Any questions? Dan?
Okay, you asked what would you say to a 15-year-old girl. Okay, what would you say to a 15-year-old boy or a 20-something-year-old man who's having difficulty dealing with the presence of women and their advancement?
Right. Get over it. I mean, they're two very, very different people that we're talking about here.
They may be the same because the 20-plus something might in fact be mentally a 15-year-old boy.
Yeah. I think maybe I will pass on that one. It's there's enough room for everybody, so I don't understand why some people feel that people have to be excluded in order for them to do well. But I'm not sure what I would say about it, except maybe that.
So I think that I think that you get your demographics wrong. So I think that the 50. I don't know any personally 15-year-old or 25 plus that have a problem with the advancement of women because they've grown up in a different world. I think I know 50 plus that I have a problem with the advancement of women, and I don't think that they would admit to it, you know, but I think that the expectation is that men are more powerful. And the women who are more powerful are not so easy to deal with. But I think it's a problem of the older generation than the younger generation. I hope so, at least. I mean, judging from the children I know who are, you know, children who grow up in families where the mothers were working, and some of them very successfully, then it's sort of natural. That's the way you think of it.
So we have a little gift for you. We're very grateful for your coming to Waterloo and for all you've done in the field.
And I like the pink.
This one's for you.
Is that different? Thank you. Thank you very much.
And please join me in thanking them.